Cool. So we're done with homework 1, at least schedule-wise. Homework 1 is done, turned in. You can always take feedback from TAs, revise, get rid of that echo, revise it, resubmit it, and get points back based on like comments or suggestions. And same thing, like, so this was our first assignment. If you're really stuck and we don't get to like your question, you can always add questions to the notebook and say like, hey, I can't do this. Where do I go from here? Like I understand bait, or maybe I understand nothing, right? Like I don't even know what the question's asking. You can ask that right in the homework, submit it, get some feedback, resubmit, and then get those points for the work. Just quick logistic reminder, because it's not usually how classes work. Imagine that. I would want you to like learn from mistakes. Wouldn't that be nice? Not to say that other classes are not helping you learn. I'm just saying that's the main goal here, is like try something, make some mistakes, get some errors, and then learn from that. And I don't want to penalize you for trying something new. All right. What was this about? What was homework 1 about? What did we do? Like what's anything? Like what was there anything that stood out of like a lesson you learned or a skill? Time it? Yeah. What was time it doing for us? Like why didn't we just use like a stopwatch? And like thumb's not that quick. Yeah, it's tough to get nanosecond comparisons. Yeah, that's part of it. What else did time it give us? One thing that's like different about time it versus, because there are like, you can grab the wall clock time of, and in this case we're running like a server. You can say like, hey server, what time is it? Run this operation. Hey server, what time is it? And then look at the difference. And computers keep track of time in nanoseconds. It's always integer. Like time is an integer to a computer, and it's the number of nanoseconds that have happened since, I think, it depends on what operating system you're on. I think Linux on our servers, it's January 1st, 1960. So like today's date is tracked in how many nanoseconds it's been since January 1st, 1960. Kind of weird. And then it gets all crazy with like leap years and stuff, but that's why it's always like an integer. And then to get it to an actual date and time, you have to like send it through a function. But anyway, so that time it function is purely figuring out how long is the computer actually running to get you this value. So it's like how much power it takes, how much time and energy it takes to run that calculation. Cool. Time it. Have you started project 1? Taking a look at it? No? So, and that's okay. We just like turned in an assignment. It's kind of like the next day, like next day, now we're on to something new. Not logged in again. Keeps logging me out. So I'll load that up. Yeah, it's funny. I don't ask you to time anything in the project. But let's take a look at these three. So there's like intro to the problem, and then there's kind of like the three deliverables. So based on what you've done in homework 1, I'm gonna walk around and see like what are some things like what are some skills that we used in homework 1 that we could use here on project. That's the first step. It's like, do we know how to approach this problem? So I'll walk around, see what people are thinking. Then if we want, we can jump right in and try something. What should we do for this? Is there anything that looks familiar from homework problems? It's kind of same questions here. Still thinking about it. It's okay. Kind of like the last question. Yeah. It's the same exponential function, just going down instead of up. Yeah, that's okay. Yep. Okay. Yeah. Yeah. That would be great. Is it converging? Yeah. Yeah. Sure. Yeah, that makes sense. There's some kind of, it has some kind of exponential function.
I took my first art class in college. I said, "Well, I
And there's just a
So if you're plugging in like an actual exponential function, that one is a solution to that actual differential equation. So it's never going to change.
okay.
If I have 100 time steps or 1 time step, the end result is still the same.
Right. Okay, so then A is kind of like a so that integration converges. So your
Integration, it's like Euler integration. That's what we did in homework 3, where we were looking at the growth of the population. Like K times current population is how much it will change. We do the same thing here, but instead of growing, we're going to decreasing. The temperature drops all the time.
because when I'm not used to time step, just because
Yeah, it doesn't do anything, right? Yeah, yeah, because you're always plugging in the same function.
Right.
Yeah.
Okay. So then that's basically
No, you're supposed to do like to fill in all the Euler integration steps. Yeah. I mean, I saw them, I'm sure they're like even more half-baked than they used to be. Yeah. Part of it, a lot of conspiracy is grasping at straws. You're having so many people that are they're in on the secret. You can't even let them hear. It's hard to see like a coffee shop in secret. How that many people would be able to come out. And I know the new inventory government and politicians, none of them would be able to keep that on top of it. I think even though it's boring, like somebody told me they had access to data that even the president couldn't have access to. So boring. It's just bad. When I first met you, it would be like looking at scheme tables for vacation data. Like, all right, it's helpful if you're doing it for an isolation, but most people wouldn't have anything to do with it. All right, so two things came up as we were kind of taking a look at this. Some people are kind of plugging in some values, trying to figure out how to do this. One was like, we're doing Euler integration and we have an analytical exponential function. And this one came up a couple of times. It's like exponent. I know we created exponential functions with Euler in homework 1. And we did it twice, right? Like in one case we were looking at truncation error from Euler integration in this first part, and then in the next one we were looking at truncation error of like an actual exponential function. So this one was more of like a math problem of like how well can the computer represent like pure math. This first one where we're looking at population growth and differential equations, that's a little more like applied math, like engineering stuff. We see that a lot more. It's like I have this differential equation, it's doing something, how do I figure out what happens next? And that's kind of what we're doing here in the project. Other part that came up was like we're using Python to calculate things and then we're trying to make a function out of that, which is exactly like the first couple of things we did in the homework was just trying to figure out how do I create like a reusable set of functions. Like so again, it's not required. It doesn't say like create a good doc string, but doc string would be helpful so that you know something like, what are the units that are involved here? Is this measured in hours, nanoseconds, seconds? What is the temperature in? Are you using ranking? Did you convert to Celsius? Things like that. Cool. So getting started. Project 1. I'm going to delete my stuff. And then I can either like show some stuff, or if there's like questions about this to start. Is there any question so far? Here's one for you. What is a finite difference approximation? Sounds like a real fancy word that we haven't said that at all in this class until now. Finite difference approximation. Yeah. So we have 2 data points, and you can't take a derivative of a number. Like if someone tells you it's 75 degrees out and you ask for the derivative, it's like, I don't know, 0? Like it's 75. But if I know that it's 75 now and it was 74 an hour ago, rate of change was on average 1 degree per hour. We can do the same thing here. And really what we're doing is like, we're taking all that, the first, I'm trying to remember. Usually it's like the first week or 2 of calculus, you spend a lot of time doing limits. Do you remember doing limits in calculus? Forget everything you knew about limits and undo it all, because now we're going to say, undo the limit. A derivative is just delta y over delta, or delta f over delta t, like an actual time step. So what's my change in temperature? The rise, because that's what we need. We're calculating a slope and saying slope is derivative. – 80 minus 85. Like that. Looks right? No, at least no one like, no. What about change in time? What's the run? So we have rise, a negative rise. What's our run? How far did it? 45 minutes? Should we call it 45? Like that? Yeah. Elapsed time in hours. Yep, T is elapsed time in hours. So maybe we should put it in hours. So divide by 60. Yep. So negative 6.66, so 6 2/3, around 7 degrees per hour. It's like what we were dropping for that first 45 minutes. It's got to change, like it is an exponential function, so this is just the average over that first 45 minutes. How do I calculate K? Yeah. Yeah, we could take this, put it over here. So I'll take this part. I'll put it in parentheses, just for good measure, and divide by, since we have that negative sign, just flip it from TA minus T, that works. And so we got 65 minus 80 or 85? Which one's T? $85? So we'll call T of T plus delta T. All right, so we've got time, 0, 3/4, and it's like 1, 2. Again, have 2 data points. The only thing we can do with 2 data points is draw a straight line. So that's our slope. The question that we're asking here is this slope the slope at time 0, or is this slope the time at 45 minutes? Because the slope is changing. There should be a new slope at the next time, or the next set of 2, right? So where do you want this slope to be true? Time 0 or time 45? Bless you. Who says time 0? Nobody? Yeah, time 0. Time 0, yeah. Who says time 45 minutes? 45 minutes, yeah? Yeah? You're both right. Like, there's no, there's 2, both of them have the same amount of error. Like, we're taking an exact derivative and approximating it with slope. That introduces truncation error. Like, it just has to. So both of them are wrong by the same amount, so they're both right, as right as we can get. They're both different answers. Both of them, like, 85 is not 80, so it is a different value. but it doesn't really matter. We'll get back to this like module 4 again, or sorry, module 3, but it's the difference between a forward difference approximation and a backward difference approximation. So are you saying that like, are you using the next one to approximate derivative, or are you using the previous one? If you're really hung up on this, like, no, I can't deal with this, it should be more accurate, then you can make it more accurate. You could do both and take the average, and now you reduce the error by a little bit. All right, so I'll do 85. 1/3. What are the units here? Because I just calculated like K. Yeah, so this is like a 1/hour unit. And in the beginning, we talked about like, should we use minutes or hours? If we used minutes, it would be a 1/minute unit, which kind of a weird like heat transfer unit, but it works out because change in temperature over change in time, it's like Fahrenheit over hour equals something times change in like difference in temperature, so Fahrenheit. So the thing to make it match has to be 1/hour. So we don't have any, there's no watts here, there's no area. All that's taken care of with just like one, it's called the time constant. Just K is our time constant for how things are changing. I think I deleted question 2. All right, so if I want to get the same answer, 1/3, how do I make a function that will take some inputs and give me the same thing? What do you think that'll look like? Python doesn't do that anymore. If you ask for 2/3, it gives you 6, 7, even if it's log 2 and 3 were integers. But it used to be if you think like Python 2.6, it would give you a 0. Yeah. Oh, like when I, whether it's 0.3, I think the other numbers like 0.4.
But it's still wrong. They're still right.
Yeah, they're both equally wrong. Yeah. But they're as close as we can get with the data we have. There, I've seen like a handful of people, because you know it's an exponential decay, you could like plug it into the function and solve e to the 45 minutes plus e to the exact. And then you get like much closer to the a value. It's an approximation, and it's fine. We do it all the time. At least for engineers.
So how I find where the
Oh, like looking at intersections. Right. So it never actually like intersects values. Yeah.
I was like trying to find upper and lower bound over 85 and sort of average it.
I mean that was one. Another way is so is your initial temperature 96 now?
Yeah.
I'm trying to figure out how much time.
Yeah.
So one way to do it is your start time is 0, initial temperature 98.6. Your end time, call it 1 hour. Goes 0. Now it goes 98.6 to 83. Okay, that's too low. Okay, 55 minutes. Now your end temperature is 84.5. Right, that's pretty close to a little lower. Yeah. It's still a guess and check method, but you can get to an exact 85. Yeah. Yeah, we could look at finding methods which automate that process. How do I get numerical image and where it wants to be? That's what you're describing. Yeah. Oh, okay. Were you doing the same? Okay, just curious. Cool. You make like function. Okay, yeah, yeah. Good, good. Oh, you're all done?
Yep.
Oh, okay, nice. Cool. So when at least this is my process, is like, if I can get something to work, I just copy all the code that worked for me, put it into my function, and then start figuring out like, all right, am I doing too much? Do I not need to do this? So here, when I calculate this dt, I don't, at least in this case, we always want it to be 80 and 85, but it could be something else. Like if we want to reuse this the next time someone finds a corpse in an NCSI sort of episode. So I could say this is T0, and I could call this one T1. DT, I shouldn't have to calculate this since I'm already inputting it. And I'm gonna show like a little trick that's kind of nice, especially when you're gonna run the same function. I can set default values. And that way I can run this function without any input, and it's going to use these 3 inputs for me. And again, you don't have to do that, but sometimes it's nice, especially if you have like 6 different variables. It's nice to have some defaults so you're not typing in each variable every time. This one, not a huge difference. And then I don't have to calculate this dt over dt again, so I'll comment that one out. What's the last thing I need for my function? The last line. Every function needs this last line. Return. Yeah, you always need, the function it doesn't end until you have a return statement. So you need that return. And I'll return K. Oh, I should use, let's add an ambient temperature, right? Oh, syntax error. I forgot the comma. Oh, I should use T1 minus T0, right? So I have rise over run rather than negative rise. Now I get the same value that I got before. Then question came up of like, well, can I use T1? Like, is it okay to use T1 here? And we could add another input of like, So now I'm giving myself the option of like, do I want to use a forward? Do I want to use a backward? And I can run this. Now I could actually compare them. Oh. If I could spell, then I could. Now I can see the difference of like, should I use forward? Should I use backward? Should I take the average of them and use like something like, I don't know, what would that be? 0.39, 0.37? And again, I'm a big proponent of doc strings, of like being kind to your future self. Whenever you go back, you want to go revise this work. A doc string does a lot to help you out the next time you revisit this function. Like, why do I have an if statement when I'm just doing a simple derivative calculator? What's happening here? And as a first start to get, let's sign in. I mean, we can use the learning coach. We'll learn about a topic. So here I pulled up the learning coach. I gave it my function and said, help me write a doc string for this. And it might not be perfect, but it might give me the right format, and then I can go in and edit it the way that I want it. So I'll copy that code. And let's just make a whole new cell below here. Paste it in. Oh, it deleted my... So in here, it does a good job of like at least putting it in the right format of like, hey, there's parameters, there's a return value. The only thing that I would add here is that these are, I guess technically they're optional, but I would say like in degrees F. So then I have like something to tell me like what is the temperature actually in. Okay, cool. Thanks for coming in for Friday morning, and we'll be back Monday morning.